Welcome to Dr. BT's Chemistry Essentials, A-level chemistry made easy. In this video we're going to be looking at the idea of empirical formula and, importantly, elemental analysis. Now, the elemental analysis has strong links with elucidating or determining the structure of an organic compound in the organic analysis type questions that you get in the exam. So we're going to look at the principles and then we're going to focus on the application of this in these types of questions. So firstly, we must start by defining what an empirical formula is and its difference compared to a molecular formula. So an empirical formula is the formula giving the simplest whole number ratio of all the atoms of each element in a compound. This is different to the molecular formula, because this shows the actual number of atoms of each element in a molecule or compound. So if we took the alkene C3H6, this would be its molecular formula, because this is exactly the right number of carbon atoms and hydrogen atoms. But its empirical formula would be the simplest ratio. So if we have 3 carbon atoms to 6 hydrogen, the simplest ratio here is 1 to 2, and so our actual empirical formula will be CH2. Obviously, the molecular mass links to the molecular formula. So if we were to focus in on C3H6, the molecular mass of this, the MR, is 42. If we were told that we had a compound that had a molecular mass of 46, and we can get this from, say, the mass spectrum, and if alongside this we were separately told or were able to work out the empirical formula was CH2, then what we could do is, if we worked out the mass of this unit, of this simplest unit, so 12 plus the 2, 14, and for how many times that goes into our molecular mass, that tells you how many times you need to multiply this unit by in order to get to the molecular formula. So for example here, we take the empirical mass 14 and we would divide that by the MR 42. That goes into 42 3 times. So we would know that to get the molecular mass from here, we would have to times our ratio by 3. This is really useful because then once you've got the molecular formula, it helps you narrow down what the structure might be. The rest of the video is going to be focusing in how we actually determine the empirical formula to begin with. Now, to illustrate why this is so important as a skill in both year 1 and year 2, take for example this structure analysis question. You can see there's 3 pieces of information here. We've got elemental analysis, which this video deals with, we've got infrared, and then we've got mass spectrometry. Now, in order to understand how all these data links, you need to have all 3 pieces of information to work out the structure. And elemental analysis is highly linked to mass spec because of the fact that on your mass spec here, you have a peak that tells you the MR. If you can work out the empirical formula here, you can use the equation shown here in order to work out the molecular formula. So we know the MR comes from this peak, the one furthest right on the mass spec. What we need to now focus in on is how to work out the empirical mass. Well, we need to work out the empirical formula, and this comes from this data here. So that's what we're going to turn our attention onto now, so that you can answer these longer type questions. So to illustrate this method, we're going to look at this snippet of a question here. This came with extra information, so in infrared and some mass spec data, but we're just going to focus on this elemental analysis here. So we've got some percentages. Now they should add up to 100%. As a matter of fact, they're actually slightly over this. They're 100.27%, and obviously this is just due to the practical nature of the subject. You're not always going to get it completely accurate, but what it does tell us is that we only have carbon, hydrogen and oxygen in here, as it adds up to roughly 100% exactly. Our first step is going to be calculating the amount of moles of each of the atoms by dividing the percentage or the mass given by the atomic mass of each species. Here we've been given that carbon has 54.54% of the sample containing carbon, and its atomic mass, as found on the periodic table, is 12.0. Same for both hydrogen and oxygen too. You just calculate each of these. Now you can see similarities here that you've got basically it's just mass divided by mR. So N equals M over mR. But it's slightly different here because we're dealing with elements and their atomic mass. Also here the data given is percentage by mass. But if this was just mass of carbon in the sample, mass of hydrogen in the sample, and mass of oxygen in the sample, then that would follow the exact same method. With these values, the second step is to take the number of moles of each of these elements and divide it by the lowest value of the three. So for example here, this value here, 2.2725 is the lowest, so we're going to divide each of these numbers by that value. Step 3 involves taking the answer of step 2 and rounding up to a whole number if required. In this case it's quite obvious, so we've got 2, we've got 4, and we've got 1. Something to note at this stage between step 2 and step 3 is if on step 2 your answer is 0.5 on any one of the elements, then you should multiply everything by 2. Just taking this for example, if it was 2.5 at this stage, you'd multiply this by 2 to get 5, then you'd multiply this by 2 to get 8, and this by 2 to get 2. Also, if you find that it's 0.33, then you times at this stage by 3, and this will give you a whole number for each of them. So it's really key that at step 3 you have a whole number. After step 3 you have the empirical formula. In this case the empirical formula is C2H4O. As previously stated, we can use this empirical formula and the mass of it in conjunction with the molecular mass, the MR, to work out the molecular formula, because the empirical formula, the mass of that divided by the molecular mass, MR, will give you how many times you need to multiply the empirical formula in order to get the molecular formula. Obviously in this question we're not given any information for that, so we don't need to do anything with this one. So what we've got here is an exam question. Now the mass spectrum data that is given with this molecular iron peak at MZ97, that is your MR data that you can use in order to get your molecular formula. So you're going to calculate the empirical formula from this data, use the MR to then generate a molecular formula. So pause the video here and have a go. First of all, we've got our elemental analysis data here. So we're just going to lay that out in our grid. And we can quickly check that all of these percentages add up to 100%. So we know there's not a fourth element that's involved in this compound. So it only contains carbon, hydrogen, and nitrogen. Then we do the division over the atomic masses that are just taken from the periodic table. Then we just divide each of these values by the smallest value out of the set of 3. And that gives us the following. And we can see here that we haven't got any 0.33s or 0.5s, so we're just going to round down or up. So this will be C6, H11, and M1. And if we add up the mass of this empirical formula, that equals 97. And we can see that matches the MR that's taken from the molecular iron peak at 97. So we know the empirical formula in this case is also the equivalent as the molecular formula. So this would then allow us to work out some extra structural features, etc. So in this video we've looked at empirical and molecular formulas and worked out exactly how to come up with an empirical formula from 2 examples that demonstrate percentage compositions, so by percentage. We've talked about the fact that mass in grams would be exactly the same. All you have to do is the same method. And then what we've done is talked about the context in which this is used in both year 1 and year 2 organic chemistry in order to help deduce a structure of an organic compound. If you found this video useful, please like it and then ensure that you subscribe to the channel for new videos as and when they're uploaded.